Hello everyone, my name is Krish Giridhar and I wanted to welcome you all to today's webinar. Before we get started, some housekeeping tips. You can type in your questions using the chat window anytime during the hour. We'll try to answer your questions during the session, and we will also have a short Q&A towards the end of the webinar. If we're unable to get to your questions, we will send you an email response right after the session. Also, we are recording this webinar and we'll make it available via our website in a couple of days. And you will receive an email as soon as the webinar recording is uploaded. And as a reminder, this is the second webinar on this topic. The first webinar was held on May 24, and the recording is available on our website. Okay, so let's get started today. The focus of today's webinar is CAM for Jewelry, Part 2, and we plan to cover the following topics. Programming cutter paths for machining rings and bands using 4-axis methods. And then we will take a look at how we can program ring blanks using 2-axis turn roughing and finishing methods. And then also finally programming ring molds using indexed and continuous 4-axis methods. Before we get started with the demo, let's just go through a few techniques and examples. And mainly, we are going to be talking about 4 techniques or methods that are used. The first is 4-axis projection, which was covered in the first seminar. And Uday will briefly recap when we get started. And then we will discuss wrap machining, followed by 2-axis turn machining using our turn module, and then finally true 4-axis methods for machining molds as well. And in the following slides, we just have a few examples, the first one being one for wrap machining of a band. And as I said earlier, Uday will show you some examples of this as well. Then on the next slide, you can see that we have used our turn module to machine the inside and outside of the ring blank, followed by drilling of some holes, and then followed by 4-axis machining of the geometry itself. And Uday will cover this as well. And on the next slide, you'll see an example of true 4-axis machining of the mold. And that would be the last piece that Uday will cover today. So with that introduction, let me turn it over to Uday.
Thank you, Krish, for the introduction. Hello, everyone. Good morning, good afternoon, or good evening to you folks, and thank you for joining us today for the webinar series for our AMS customers. And today we'll be talking about CAM for Jewelry Part 2. Before we get started with the Part 2, I just wanted to do a quick recap of what we covered in our Part 1 series of webinar that was held in May of 2017. For those of you who couldn't make it, you're welcome to watch the webinar recording. And for those of you who attended, this is just a quick refresher of what we did in the previous webinar. So first we talked about how to program pendants and other designs blanks using 2 and 3-axis methods or 2.5-axis methods. So we talked about programming pendant designs using 2-axis methods. These are in our mill modules. We have methods like facing, pocketing, profiling. So we programmed a pendant using 2.5-axis methods. And you could program this right from our standard configuration. So standard, expert, pro, and premium, all of these have access to 2-axis or 2.5-axis methods. Now, we also talked about how to work with ring models in here. And one of the things we covered was 2-sided machining of parts of rings, the actual rings, which could be machined out of wax, and you could be doing like an investment casting process. So we did talk about how to orient the part, create a support structure so that the part can be machined from two sides, and once it's machined from two sides, top and bottom, we also talked about how this can be programmed on a rotary axis or a 4-axis using a 4-axis continuous method. So the example that you're looking at here is where we talked about how to program this part from two sides. So we have these supports that have been created in addition to the fixture. So this fixture would be the one that would basically go into your rotary axis once the part has been machined from two sides to do the finishing along the rotary axis. So here we have two setups. We've also defined the machine tool as a 4-axis, so it could be indexed on your rotary axis, and you could be using like a fixture to hold this stock blank, and you could be machining from different orientations. So I do have a representation, a picture of the fixture, what the fixture might look like in here. So for example, if you take a look at it, this could be one of the fixture types you could be using to machine it from two sides. And we did talk about this in detail in our part 1 of the CAM for Jewelry webinar, so you're welcome to go back and review the webinar for each of the programming steps. So we looked at how to start programming using a roughing operation, and then we programmed the holes for these fixtures using hole profiling operation, and then we did the roughing of the part from after flipping it over by 180 degrees, we programmed a roughing toolpath followed with finishing from the bottom side, and then the finishing of the top side in here as well. So once the part is programmed from the two sides and machine, you would be then able to break these supports on the exterior of the ring model, which can then be oriented on the rotary axis to be able to program a 4-axis continuous toolpath. And this is what we're going to be taking a look at right here, is being able to program it on a continuous 4-axis setup, and the part is going to be held on the end of the fixture. Again, I'm going to go into the layers and display the fixture so you can see how the part is going to be fixtured. So this could be one of the fixture types. You could be designing your own fixtures for it and designing the appropriate support structures for holding the part for rotary machining. So in this particular step, we talked about how to use a continuous 4-axis method to program around the entire part. So it's using a 4-axis continuous method. Now the 4-axis indexed and continuous methods are available right from our expert configuration. So if you're using expert, pro, or premium, you could be programming continuous 4-axis as well as index 4-axis toolpath methods. So this is how you can actually program the actual ring models using indexed and continuous 4-axis methods. The next thing we talked about in our last webinar is how to actually program two halves of the mold for the same ring model in here. So you can see that we've created two halves of the mold from the ring design we had, and we programmed these using combination of 2 and 3-axis toolpath methods. The first thing we programmed was the first half of the mold, and we programmed the holes using a pocket operation, and then we programmed the cavity of the mold using a roughing followed with a re-roughing operation to go back and clear out materials that couldn't be machined with a larger cutter. The re-roughing operation is available in Pro and Premium configurations. And then we did finishing, pre-finishing, and finishing operations using horizontal finishing, parallel finishing, and then finally using a pencil tracing operation in here. We repeated the same process for the other half of the mold in here as well, as you can see it. So we have the roughing operation to clear the material around these pins, and then we have 3-axis roughing and re-roughing, followed by horizontal finishing, parallel finishing, and pencil tracing. So we were able to also learn how to program two halves of a mold using a combination of 2 and 3-axis methods, which are offered in our standard through premium configurations of the product. Now some of these methods in here are part of the advanced 3-axis module, which is included in Pro and Premium, but the other methods, whereas the 3-axis horizontal roughing, parallel finishing, horizontal finishing, radial, and spiral machining are offered in all configurations starting with the standard configuration. Now we also looked at, in addition to this, we also looked at how to program a mold for a jewelry application, which could be, it could be a pendant design mold as well, similar to what we programmed a ring mold. Here we used methods like horizontal roughing to rough out material in these cavities in here, followed by clear flat tops machining to machine the flat areas, and re-roughing to rough out the areas where the larger cutter could not get into, and followed by a 3D offset pocketing, which can be used as a finishing or a pre-finishing operation. So this is just a quick recap of what we did in the part 1 of the CAM for Jewelry webinar. I would encourage you to go back and review the entire webinar recording to get a detailed step-by-step on how we actually accomplished these in RhinoCam, or you could do the same process in Visual CAD/CAM, or if you're running our plugin for SolidWorks, you could use the same as well. So today we're going to focus on part 2, where we're going to be talking about rotary machining as well as wrap machining, and we'll also take a look at 4-axis continuous methods. Folks, if you do have any questions during the webinar, you're welcome to post them in the questions panel, and we'll try to get them answered as we go through the webinar here. So the first thing I'm going to be covering here is how we program 4-axis wrap programming methods. Now some systems they call it wrap machining, where you just have to have the geometry that you're trying to program just laid out on a planar surface like your XY plane, as you can see right in here. So here I'm going to be first illustrating how the wrap and unwrap works in CAD, and I'll also talk to you about how it's handled in the CAM programming side of it. So typically in your CAD application, you can use the wrap and unwrap feature to wrap geometries onto a surface in here. So here I have a bunch of curves modeled in here, and I'm working inside of Rhino. So I'm going to show you how we could wrap these curves onto the surface. So in Rhino, you can go to curve from objects and use what's called apply UV curves. And now I'm going to select all of these curves in here that needs to be wrapped onto the surface. I'm going to select the curves, and I would like to wrap it onto the surface over here on the top. So I selected it. You can see that the curves are now being wrapped onto the surface. So the way we handle the programming of 4-axis toolpaths, the wrap method toolpaths, which are 4-axis facing, pocketing, and profiling, is you would actually be able to select the curves directly off the model surface itself. You can select them. So once you select these curves, when the toolpath is being computed, it initially unwraps it, similar to what you see here, onto a planar surface or onto a plane, and then once the toolpath is computed, it wraps it back. Now in some of the other systems, you would actually have to just select them in an unwrapped format, but the nice thing in our CAM product is you're working with directly 3D geometry, so you could select the curves or surface edges directly off the 3D model, and the CAM part of it will take care of performing the unwrap, computing the toolpath, and wrapping the toolpath back onto the surface. So we wanted to give you a true 3D representation of what you're actually going to be programming, so it makes it easier for you to also visualize the same thing in the simulation process as well. So you would be able to directly select these curves as your part regions when you program your toolpaths inside of RhinoCam or Visual CAM, or even Visual CAM for SolidWorks. You can directly select those curved geometries as your part regions for programming these toolpaths. So I'm going to now show you an example of how this is being done in the CAM. So here what we looked at is how the wrap and the unwrap technique works in CAD, and also we described to you how it's done in the CAM side of it. So now let me go ahead and bring in an example in here, and we'll program a toolpath that would involve wrapping and unwrapping in here. So the first part I'm going to look at is called Band Design 1, and I'm going to go ahead and load this part in here. As you may also notice this part in the presentation slides. So here you can see that the part has pockets, and these pockets have been actually modeled into the solid model itself. Now you could have it modeled, or you could just have these curves wrapped on these surfaces. You really don't need to have the pockets designed into it, but if you have it, that's great for visualization and for your simulation purposes. So we have these wrapped onto the surfaces in here, and now we're going to go through the process of programming it. The first step is you go into your milling browser, and under the machine tool setup, you would like to make sure that you have your number of axes set to 4 and also your configuration. So we're going to be working with rotary tables where the part can be turned. So we have the configuration set to a table right in here. And you also want to make sure your rotational axis is defined. So typically in 4-axis, you'd either be defining your rotary axis either along X or Y. In this particular case, the part is oriented along the rotational axis on the X-axis direction, and we've set it to X. So make sure you orient it according to how your machine tool is set up. So most machine tools, the rotary axis could be on the X-axis. On some machine tools, they could be set up on the Y-axis. So you need to reorient the part as needed and establish your rotary axis and the rotation center. Now in the next step, we would want to define our stock in here. So I currently have a predefined blank for the stock where this stock blank is hollowed out, and I have it created and saved in a different layer. So I'm going to make that layer visible in here, and I'm going to select the object, which is our blank right in here. As you can see, the blank is basically just like a tube stock. So I'm going to highlight this and go to stock and choose stock from selection. So now the stock is being defined, and I will go ahead and hide the blank. And as you can see here in the Simulate tab, your stock blank is defined. So we did a stock by selection. The stock from selection is offered in Pro and Premium configurations. If you're using Expert configuration, you would be able to define it as a cylinder stock as opposed to stock from selection to run the verification. So you could do a cylinder stock where the stock would basically be just a solid cylindrical blank as opposed to being hollowed out on the ID. So once you have the stock defined, in the next step, we would like to program our toolpaths in here. So I would like to program these pockets, and I'm going to program them in 2 different operations using 2 different tool types in here. So to program them, the first step I'm going to do is go into 4-axis, and I'm going to choose pocket machining. So these are similar to how we program pocketing, profiling, and facing in 2-axis, but these are wrap methods like we talked about just a few moments ago. I'm going to use pocketing in here. And in the 4-axis pocketing operation dialog, I'm going to choose select curve regions. Now these are the part regions I'm going to be selecting for machining. So I'm going to go ahead and select these curves around the edge of the part. Now I could be selecting curves, or I could be even selecting surface edges from the model. So if you have multiple curves or surface edges, you could select them from the part directly as your part region or the drive geometry for programming these features. So I have these parts selected. Now to make your selection process easier, you could use select by layer, select by color. If you have these pocket regions assigned in different colors, you can take advantage of those selection techniques available in the host CAD system, which could be Rhino or it could be Visual CAD CAM. So I have all of these regions selected right in here, all of these 7 curve regions selected. In the next step, I'm going to go to the Tool tab to make a selection for the tool, and I'm going to be using a 1mm ball mill to program these pockets, since these are fairly small sized rings. And I'm going to go into the Feeds and Speeds tab to load the feeds and speeds from the tool. And then in the Clearance tab, you'll notice that the clearance is defined as a clearance, cylinder clearance. You could choose automatic, or you could even specify stock max plus a radius. In this particular step, I'm just going to use a 2mm radius around the part, so the clearance would be 2mm above the cylinder, above the stock or the part cylinder in a definition. And then I go into the cut parameters where I could specify the global parameters. These parameters are defined very similar to how you've done in your 2-axis pocketing operation. You establish your tolerance, stock, choose your cut pattern, your cutting direction, establish your step over, and then you can specify your cut levels in here. So you can specify the total depth of cut, and you can specify your rough depth and depth per cut in here. So I would like to break this up into 2 passes, and I'm going to split it up into 1.35 millimeters per cut. And these are basically radial cut levels that you're looking at in here. And then you can also establish your entry and exit for pocketing and then pick generate. So the pocketing toolpath is computed. So as we talked about here, the curves are unwrapped, the toolpath is computed, and then wrapped back. So everything is done automatically, and you can see how quickly the toolpaths were generated, and all of the computation is taking place within a very quick amount of time here. So the 4-axis pocketing toolpaths are generated, and also your rotations are automatically computed. The degrees, the angles are automatically computed. So when we post-process the toolpath, you'll be able to take a look at the posted output, which shows the angle values as the part is being rotated on the rotary axis. And since I chose depth first on the cut levels, the pockets are basically programmed to the total depth before it goes from one pocket region to the next pocket region. As you can see, there's 2 levels being programmed on each of these pockets. So parts like these can be programmed for, toolpaths like these can be programmed for parts that have a constant radius. And for the wrapping and unwrapping, the system you computes based on the radius of the part. So the radius of the part geometry is known, and that's basically taken into account for wrapping and unwrapping. So if you have parts that have a constant radius like bands or rings like these, you could use the 4-axis wrap methods, which could be 4-axis facing, 4-axis pocketing, 4-axis profiling. Now the projection method we talked about in the first webinar, which is 4-axis parallel finishing, can also be used for parts that do not have a constant radius, like the ring models we looked at earlier. So for 4-axis facing, pocketing, and profiling, we would be needing to have parts that have a constant radius on these. So there's the simulation of these pockets as you're seeing it. And again, folks, if you do have any questions, you're welcome to post those questions in the questions panel in your GoToWebinar, and we'll try to get those answered to you. So once we have these pockets programmed, I would go back and program the next set of pockets using a taper tool in here, since there are some tighter areas which I can't get to with a ball mill. So to make my workflow simpler and easier, I'm going to make a copy of this operation, right-click and copy and paste it. And now I'm going to modify these, remove my current selections, and go ahead and pick the other regions right in here. And you can use your control key to drop a region that you do not want it to be selected if you accidentally selected it. So I'm going to select these regions right in here as you notice it. Or I could be using select by color if I had them assigned to different colors. Or I could also use select by layer, or use one of the other selection techniques that are available in Rhino or in VisualCAD. So I have all of these regions now selected. I'm going to swap my tool to a taper tool in here, and leaving all the other parameters at the current settings, select generate. And this would create the pocket toolpaths for the other features that are on the model. Again, it uses the wrap and unwrap. So it unwraps the geometry, creates a toolpath, and wraps the toolpath back onto the model. And there's the pocket toolpath being programmed with a taper tool or a conical tool. You could always select pause and then pick simulate to end to run through the simulation. At this point of time, I'm just going to hit pause so that we can go and cover some of the other topics in here in today's webinar. So again, once you have these programmed, we could switch back to the program tab and then post-process the output. So I'm going to right-click and post. And for the post processor, I could be selecting a post that's applicable to my machine tool. And I'm just going to go pick a FANUC control in here. I can select the post from the list and select post. And the posted output file would now show up in a text editor, which could be a notepad or a text editor of your choice. And as you can see here, the rotation angles are automatically computed and output in degrees. So you wouldn't have to manually compute or index them. They're automatically computed based on the curved geometries that you selected for programming your 4-axis toolpaths. I'm going to go ahead and save this file out. The next thing we're going to take a look at is how we could program a 4-axis profile toolpath. So you could have a band design, a ring design you could be using like for features like these on the part right in here. I'm going to use a similar process to program it. So I'm going to first start out by defining a stock blank in here. So I have it on a layer. I'm going to just highlight it and use stock by selection. I could do a stock from selection, so there's your stock blank that's being defined. Now if you're using a standard, the expert configuration where you can do a stock by selection, you could just do a cylinder stock in here and use copy model bounding cylinder. It would define it as a cylindrical blank. So you can see the hollowed out stock, but you can still use for the purpose of verification or simulation. Now since I have a stock defined in here and I have access to the Pro and Premium configurations, I'm going to do a stock by selection. And I'll hide the stock blank that was modeled in the CAD. So we now have this part in here. As you can see, the part has these profiles cut out on it to create a pattern on both sides. Now again, this is a band with a constant radius, and I would like to profile cut these shapes around the part. I have 4 of these on each side. So the workflow would be very similar to what we did in the previous example. Instead of using a pocket operation, here I'm going to use a profile operation. Again, go in 4-axis and choose profiling and select these curve regions. You could select them by layer, or you could just graphically select them. You can be selecting either a surface edge, or you could be selecting a curve to make your selection process. In the next step, make a selection for the tool, and in this particular case, I'm going to use a 1/8" end mill, establish feeds and speeds, and you can establish your clearance. In this particular step for the clearance, I'm going to just put it 100 thousandths above the stock max. In the cutting parameters, you can establish a cutting direction, whether you want to climb mill, conventional, or mixed. I'm going to use mixed cuts, and for the cut start side, you could choose right or left for the cut start side. And since I need to program a larger cross-section area here, I'm going to use the total cut width in here and specify a total cut width of 100 thousandths, and we'll use a step per width of 50 thousandths. So I would like to step it over in 50 thousandths passes and start 100 thousandths away from the edge of the part. And then in the cut levels, I could specify my total cut depth. This would be your radial cut levels. This would be 100 thousandths, and I'm going to basically split this into 2 passes. So I'm going to go slightly deeper to clear the material. So I'm going to change it to 1/8 of an inch, and we'll split it up into 2 levels of 1/16 of an inch each. And you can also establish your entry and exit parameters in here to how you want the cutter to lead in and lead out. And this is very similar to what you've seen in your 2-axis methods, where you can specify your entry and exit options. Very similar to 2-axis profiling, and you could apply entry and exit for each cut level. So again, it does an unwrap, computes the toolpaths, and wraps it back. And there's your 4-axis profiling toolpaths. Now let's go ahead and run a verification. We'll switch to the Simulate tab and select Play. I'm going to slow down and rerun the simulation. So if you want to slow it down, you can use these slider controls. In addition to that, you can go back into simulation preferences and use Simulate by distance and specify a display interval value to further slow down the simulation. So there's the profile cuts in 4-axis, and by specifying a total cut width, you're stepping it over 50 thousandths on each cut. So we now program the profiling for one of the sides. We could go back and repeat the same process for the other side. So I'm going to copy and paste the operation. You could use Control-C, Control-V, or you could do a right mouse button click, copy and paste, and go back and reselect the geometries in here. So I'm going to pick the geometries over here on the other side. As I pointed out earlier, I could be selecting either surface edges, or I could be selecting a curve region. So in this particular case, I'm going to use a curve region, as it just makes it easier rather than having to pick multiple surface edges. Now you could use your curve extraction tools in the CAD program, like duplicate edge, duplicate face border, or other tools to create these curves, and then you can chain them or join them together and select them for programming your toolpaths. Now when post-processing these toolpaths, we now have the ability to output inverse time feed rates. So you can go ahead and enable the inverse time feed rates. If your controller expects a G93 or a G94, you can go over to your feed rate section in here and you can enable this inverse time feed rate and select the code to toggle it on and toggle it off. So I believe G93 is commonly used for inverse time feed rate on. You can enter this parameter right in here, a G93, and a G94 is to basically turn off inverse time feed rate. So once you've established this, upon post-processing your machining operations, this would output your inverse time feed rates. As you can see, there's a feed rate being computed and output for each line of motion, each line of linear cut motion. So the inverse time feed rate is a new feature that was offered in version 2017. Again, folks, if you do have any questions, you're welcome to post those questions in the questions panel and we'll try to get them answered to you. The next thing we're going to cover is how we can program ring blanks and actual ring design patterns using combination of our turning and milling module. Now to go over this, I'm going to go ahead and bring in this part example in here, and we're going to take a look at how we could program these ring blanks using first starting out with the turning module, and then we could use our milling module to program these holes and these designs and patterns for inserting your precious metal stones like gems, and you have all these prongs in here as well. So I've actually prepared the part by creating a blank for the turning module for the turn. So the initial blank for turning, I've created these right in here. You can see that this is the initial blank. I would like to turn it, so that would be my initial stock for the finishing process on the mill module. So the first step is to go ahead and program this blank using the turn module. So I'm going to go into RhinoCam and I could select turn from the menu, or I could switch from the mill to the turn module by just clicking on the mill icon over here on the machining browser. Now folks, if you have a 2-axis CNC lathe or a turning center, and if you do have the RhinoCam's turn module, you'd be able to program turning operations. If you do have a CNC lathe but do not have the turn module, you're welcome to contact us and we can provide you information on how you can add the turning module to your existing product lines. So we have the part to be turned modeled in here. So I'm going to go ahead and switch over to the top view. Now also, we want to make sure that for turn programming, you'll notice that the coordinate system is automatically established, which means the world X coordinate is transformed to the turn Z coordinate, and then the world Y coordinate is automatically transformed to the turn X coordinate. So you just have to make sure that when you design your part and orient it, you have it in the top view or the XY plane of your host CAD system. So once you have that oriented and have the part at the back, oriented at the back face of the part, so your origin would be placed at the back face of the part as you see right here, we could now define the part for turning. So we could go into the turn module, select the program tab, and then go down to part, and you could now select the part that you'd like to turn. You could either be selecting solid geometries or surface or mesh geometries like the one that you have in here, or you could be using select curves, and if you have a curve like a cross section of this part, you could even select the curve as your part geometry. So you could either select solid surface geometries or you could select curves to define the part for turning. So now the part is defined, and as you can see, it shows part as being defined right in here. In the next step, you would want to define your stock material. The stock would be defined as cylinder, part cylinder, offset, revolve, or you could even do a stock by selection. So if you have a stock blank that's defined in here, so I have a stock blank for the turn, I could highlight this model and use a stock by selection or stock from selection to define the turn stock. So we now have the part and the stock defined for turning, as you can see it. Now, since the part that we are going to be programming has both OD and ID features, in the simulation in turning, you have the ability to display the stock model as a full or a 3/4 or a half or a quarter view. I currently have it set to a 3/4 view so you could actually see the ID features during the simulation. If you'd like to change it to a full view, you can select full and it'll automatically change the display of the stock blank to a full view as you see it. So switching it to a 3/4 view makes it easier to visualize simulation of cut material simulation in here. Now we'll switch back to the program tab. Now we've defined the part, we've defined the stock, and all of this information is updated in the turn browser, very similar to how it works in your mill module. Now the next step is to establish the work zero. So typically in turning you would establish to the rightmost face. Once you have this established, you'd want to program your operations. You have turn, roughing, and finishing operations. You also have groove roughing, finishing, follow curve, threading, and parting up. Now in this particular part we're focusing on just the roughing and finishing part of it. And for turning, you can define different types of turning inserts. We're going to be using a diamond insert for this particular process, and the orientation of the insert is critical for programming OD and face versus ID. So you can choose the orientation as you define the tools in here. So I have an insert for OD, which is outer diameter, and ID is for inner diameter. So we have two inserts defined, and there are also additional insert types that are available in turn module. So we have the work zero established, and it's set over here to the rightmost side of the blank. In the next step, I'm going to go in and program a roughing operation, select turning and roughing, and I'm going to pick the insert as OD, the diamond insert. The feeds and speeds can be set either in millimeters or units per minute or units per revolution, depending on what is expected by your machine tool. You also have a built-in calculator to help you compute the feeds and speeds in turning, very similar to milling as well. Now you can establish your global parameters. Now since the tool that we specified was an OD, or orientation was outer diameter, the system automatically sets the approach type to OD or face. Now you can't program an ID operation if your tool orientation is set to OD. So it automatically knows based on the orientation of the tool, the approach type is automatically established. So here I can either do an OD, which is outer diameter, or a face. I could then establish the tolerances for roughing, specify the stock to leave in here for the roughing operation in turning. I'm going to specify 0.05 millimeters. If you need to specify any cut containments, you can establish that. Specify your parameters like your cut pattern, your cut direction, your depth per cut on the turn roughing operation, and you can establish your entry and exit parameters for the roughing process, as well as the clearance for turning. And I'm going to set this up to 2 millimeters above the stock and then pick generate. So now the turn roughing operation is computed. The toolpaths are visible. You can toggle the visibility of your toolpath, and you can switch to the simulate tab, and you can run a verification by selecting the play button. And there's your turn roughing simulation. And the tool automatically does a relief angle prediction. It checks for the relief angle of the tool to eliminate collision or gouging with the part and the stock geometry. So we got through the process of turn roughing. Now I'm going to go ahead and program a turn finishing operation with the same tool. We'll use the same orientation for the tool, so OD, and then here I'm going to specify the start and end points to establish the direction of cutting. So I would like to start over here. I can use the object snaps in the CAD system here. I'm going to snap to the end points of these two curves. I would like the finishing to follow along from the start to the end point. Establish any additional finishing parameters in here if you'd like to do multiple cuts. Establish your entry and exit, and you can establish your clearance settings and then pick generate. So the turn finishing operation is now programmed in here since we left some stock on the roughing process. So once the finishing is completed, we would now like to go back and program the ID roughing and finishing operations. I'm going to go over and program a turn roughing, and in this particular step choose the tool as the ID insert, establish feeds and speeds, and in the global parameters you'll notice that the approach type is automatically set to ID since the tool orientation was chosen as ID, and we'll specify the parameters for tolerance, stock, any cut containments if necessary. In the turn roughing tab you can specify your cut pattern, you can establish your cut direction, and you can also establish your depth per cut, establish the entry and exits. The approach types are automatically established based on the orientation of the approach type. So for ID, you'll notice that the entry and exits are automatically set. You can set your clearance parameters in here, and you can either hit generate or save. Saving only saves the parameter settings that you put in. As you right click and regenerate, the toolpaths are being computed. So now let's go to the simulate tab and let's go run a verification. So I'm going to go into the isometric view or the perspective view and run a verification in here for the turn ID operation. So with a 3/4 view, you'll be able to clearly see the areas being roughed out. Now I'm going to switch back to the program tab again and program a turn finishing operation in here. So turning, finishing, select the tool, specify the parameters, and I can again specify the start and end points for finishing and establish any additional parameters and then generate. And there is the finishing toolpath for the ID. So once you have these operations programmed, you're now ready to post-process this. So this basically is the initial blank that would be for your milling process. You've already turned the blank OD and ID using a turning operation, which is now ready for milling operation. So you need to be able to first machine this on your turning center or your CNC lathe. So you'd want to post-process this out to the machine. So you right-click on the operation or right-click on the setup or machining job and select post to post-process your output file. And you can choose your post-processor in here. So there are a wide range of post-processors that are available in the turning module as well. And selecting post will output your posted output file. Now, if your machine expects the diameter mode output for X coordinate values, you could always set this under your preferences. You can go into preferences and go down to machining, and there's this option to choose diameter mode programming. So by selecting this, you will see that the posted code, the X coordinate values in your posted code will be in diameters as opposed to being in radius. So this is a setting under machining preferences, and it's a global preference that you can set. Now once we have this part programmed, we are through with programming in the turn module. Now we want to switch over to the mill module to program the features that we noticed, the holes, drilling of the holes, and also those pockets in the mill module. So I'm going to switch from the turn module over to the mill module right in here. So click on mill, and let's go ahead and display the visibility of the part that we have for the milling process in here. Folks, if you do have any questions, you're welcome to post those questions in the questions panel, and we'll do our best to answer them for you. So now we are back into the mill module, and here I would like to first establish my stock. So I already have the stock blank from the turning process. So I'm going to select that and define it as stock by selection. So we now have the stock defined, and we have these holes that needs to be drilled. In addition to those holes, we also need to be able to cut these slots or grooves around this part. And again, we're going to be using a 4-axis method to program all of these. So we're going to be using 4-axis drilling and 4-axis engraving operations to program this. So the workflow would be very similar to what we did earlier. So we're going to go ahead and define our machine tool. We're going to set the number of axes to 4 and establish the axis of rotation, and also define the configuration of the machine to be a table and the rotation center once we establish a rotary axis. In the next step, we've defined our stock material. Already here we've used stock by selection, so your stock blank is already defined right there. There's the stock blank that you just created from the turning process. And now we are ready to program our toolpaths in here. So I'm going to go into 4-axis, and you'll see that there's different methods in here: profiling, facing, pocketing, profiling, and also we have engraving. First, I would like to program these holes. So the 4-axis drilling methods can be found under hole machining and 4-axis drilling. Now these methods are available right from the expert configuration. So I'm going to select these drill points. I could select drill points or these circles in here as my part geometry or the hole geometry for drilling. Or you could be selecting directly face edges as well from the 3D model for your for the part regions or the holes to be drilled. So I'm going to go ahead and pick these holes from the model as you see it. So you can basically select an edge or you can select the circular geometries that are on the part itself. So I have these holes selected. Right click or press enter to accept it. In the next step, I'm going to make a selection for the tool. Now for the first set of holes, the holes are like a counter bore, so I'm going to start with a 0.78 millimeters drill bit, establish feeds and speeds, and then clearance. In the cutting parameters, you have the similar drill types that you have in your 2-axis drilling operations. You can do standard drill, deep drill, countersunk, brake chip, or you could have a user-defined drill cycle. So I'm going to go with the standard drill. I'm going to specify my drill depth in here and specify the additional parameters where I would like to make it want to go through. So I'm going to select add tooltip to drill depth and also establish the approach distance in here and then pick generate. So now the drilling operations, the 4-axis drilling operations is computed. You can see the drill toolpaths right in here, and let's go ahead and run a verification for it. So simulate, and then I'm going to hit play, and there's your simulation of the drill operations. As you can see, the holes are drilled through, and the rotation, the angles are computed automatically based on the part regions that you chose for the drilling. Now I'm going to go back and drill the next step of holes in here. I'm going to make a copy of this operation using copy and paste, edit the operation, change the tool to the larger drill bit, and in the cutting parameters I'm going to modify the depth in here for drilling. I'm going to set the drill depth, and since this is not going to be a through, I'm going to clear this checkbox and then pick generate. So this basically creates the cavity so you can insert those stones, the precious stones, into the ring once it's ready. In the next step, we would like to go ahead and program these slots in here. So for this process, I'm going to be using an engraving. This is a 4-axis engraving method. You can find this under the 4-axis methods. You'll find 4-axis and engraving. And I'm going to first select the 2 end curves. I could be selecting curves or face edges. Now this is a projection technique we're using. It's not a wrap, it's using a projection method. For this, I'm going to use a V-mill, which is a taper tool for the engraving process. Specify the feeds and speeds and clearance, and establish the cutting parameters. I would like to establish the tolerance in here and specify the number of finishing passes and depth per cut. So I would like to go in 0.03 millimeters, and I would like to create 33 passes in there and generate it. So I want to go in smaller steps since I'm using a very fine pointed tool. So the engraving operation is programmed for the 2 part regions I've selected, and selecting play runs a verification in here. As you can see, the slots are being cut using an engraving operation. You can always speed up the simulation in here to have it go faster or slower. So you could use a combination of index and continuous 4-axis methods as well to program certain features on the part. Now once we have this programmed, I'm going to repeat the same engraving operation in here to program the feature right in the center of the part. I'm going to go ahead and drop the region and select the curve region right over here. And for this purpose, I'm going to use a form tool or a user-defined tool, and I'll talk about in just a moment how to create the user-defined tool. Using the same parameters, I'm going to pick generate, and the toolpath is now computed. We'll go ahead and run a verification for it. So this basically helps you create the cavity design on your model by programming these 4 steps. We use drilling and engraving operation. Now let's take a look at how we define the user-defined tool in here. So the user-defined tool, for creating a user-defined tool, you just have to draw a cross-section of the tool profile. In this particular case, I have defined the cross-section of the tool profile with the tip of the tool being at the origin, and it's on the XY plane. So once you define or draw the tool in your CAD system in here, you just have to highlight it, go into your tool definition, and go to user-defined tool, and you just select load selected profile, and the tool is automatically defined. And you can refer to the help section for more information on how to create the tool profiles as well, or if you have any additional questions, you're welcome to write to us. Now, these tools can be used in operations like profiling, engraving in both 2 and 4 axis operations, as well as in indexed operations. So in this example, you notice how we can take advantage of mill and turn modules to programming ring blanks and the patterns and designs in the ring in our CAM product. Now, the last thing we're going to cover today would be the true 4-axis machining, and to go over that, I'm going to go ahead and bring in an example in here to show you how we could program true 4-axis operations. So what I have here is a cavity of a mold of a ring. As you can see, the ring the ring is laid out on the back side and split in 2 halves, but in this case it's laid out on the side and we've created 2 halves, and I'm going to show you how to program just 1 half of this cavity. So this is the ring model, and we have the cavity of the ring in here. Now, typically when we program 4-axis toolpaths using either the wrap methods or the projection methods, you will not be able to program toolpaths that dip below the rotation center. So to program features like these with our 2017 version, we have a very nice method called drive surface machining, where the tool remains normal to the surface being programmed, and you can pick a drive surface that could be even dipping below the rotation center, and we're going to show you how to program features like these using true 4-axis methods using the drive surface machining. The first step in programming this part would be to rough it out. So I'm going to use a method using 3-axis technique, like an index 4-axis method. So once you define the machine tool, your post-processor, and define your stock, we're going to go through the process of creating a roughing toolpath. So I'm going to use a roughing using a 3-axis technique. And in this particular step, I'll use a tool. I'll use a 1/8 inch end mill, establish feeds and speeds and clearance, and also specify my cutting parameters in here for the roughing process. I would like to leave just a 0.2 millimeter stock, specify my cut levels in here. I will go in at 30% of the tool diameter and specify any additional parameters under advanced cut parameters like arc fitting, and then choose generate. Now the roughing toolpath is being computed right in here, and you can see that the roughing operation is generated. So this is roughing in levels, or also known as Z-level roughing. Now once the roughing operation is completed, I'm going to go ahead and run a verification of this and select pause and then simulate to end to run through the simulation. Now once the roughing process is completed, now I could use a combination of indexed and continuous operations to program some of these features in here. So for example, if I would like to use just a 3-axis process to finish these, I could be using a 3-axis method like a between curve machining to finish this using a 3-axis operation. I could select curve regions in here where I could pick these 2 edge curves from the model and specify a tool for it. I could be using like a ball mill cutter and establish my cutting parameters and the step over parameters in here and generate it. So this basically creates a 3-axis operation. Again, you're just programming in a 3-axis mode so that there's no rotation axis involved in here. Now, rather than programming this as a 3-axis, we would like to use a 4-axis technique to program this, and which I'm going to show it to you here in just a moment, how we can take advantage of the 4-axis drive surface machining operation. Now, in order to program a drive surface machining, I need to have a surface that's normal to the axis of rotation. So in here, I've actually created a surface, and as you can see, the surface is beneath the part. As you can see, this surface right in here, I have it on a different layer, and you'll notice that this surface is normal to the axis of rotation, and I'm going to use this surface as my drive surface, so the tool remains normal to the surface, but it's going to be following or projected to this cavity of the mold. So to program the drive surface machining, I would go into the 4-axis methods and choose drive surface, and I need to select the surfaces for my drive surface. I'm going to use select surfaces, and I'll pick these surfaces in here, these three surfaces. Right click or press enter to accept the selections, and also it's critical to make sure that the surface normals are pointing in the correct direction. So in this particular case, you'll notice that the surface normals are pointing away from it, from the intended direction you're looking to cut it from. So I will need to flip the normals. I'm going to use flip all normals. So the normal directions are now flipped or oriented. In the next step, I'm going to make a selection for the tool, which is going to be a ball mill in here. So I'm going to pick the ball mill tool, specify the feeds and speeds, establish the clearance, and also specify the cutting parameters in here. I'm going to choose the cut direction to be across axes, and then specify generate. So in this particular step, you'll notice that the toolpath, what is generated in here, is following the surface, and the tool is normal to the surface. I need to go back and do one additional parameter selection in here. When I go into the cut parameters, I need to make sure that the toolpath is being projected to the mold cavity. So I need to make sure I select project to geometry and then pick generate. So now the tool axis is normal to the surface, the drive surface, but then it's projecting to the model. So this is one of the very nice ways how you can program using a drive surface method, even when you have features that are dipping below the rotation center. And you can effectively program features like these using the drive surface machining method, which is a new method that's being offered in 2017 version, and it's available right from the expert configuration of the product. So if you're running expert, pro, or premium, you will have access to the drive surface machining method. Now the cut pattern could be set to either across axes or along axes to program these toolpaths. Now in this particular toolpath, I've used across axis, but I can go back and change this to an along axis cut pattern. Now the drive surface I've created, I've constrained so that it stays within a 45 degree, because if I chose it to go to 90 degrees, then you might end up having collisions of the tool or the tool holder as the tool rolls over from one side to the other. So it is very critical or important to make sure that you define your drive surface correctly so that the toolpath that you are generating gives you the intended results. Again, folks, if you do have any questions, you're welcome to post those questions in the questions panel, and we'll do our best to answer them for you. So the last thing I'm going to go over here is to show you how we can switch the cut pattern from across axis to along axis, and this can be done in the cut parameters, where you can switch the under cut parameters tab, you can choose the cut pattern to be along axis. I'm also going to drop the step over down to 10% and generate it. So there is your along axis cut pattern in the 4-axis drive surface machining toolpath, and I'm going to run a quick verification. So there is the along axis cut pattern on the drive surface machining. Now let's go ahead and post-process these toolpaths and take a look at the posted code. Right click and post, and I'm going to choose FANUC as the controller. And there's your posted output file. You can see that in addition to just the, you have all 3 linear axes in the output X, Y, Z, and A, and as the tool remains normal to the surface being, the drive surface that's being machined. Now with this, I would like to hand this back to my colleague Krish.
Thank you, Uday. Okay, folks, thank you so much for setting aside this hour to join us today. This webinar has been recorded, and you will receive an email as soon as it's uploaded for viewing. And as always, we are available for questions during the week, so please do call, email, Skype, or chat with us. And follow us on Twitter and Facebook, and please keep in touch. Thanks once again.